So that is actually the so-called t-test. But before we will talk about that one, let me just walk you through first at some of the concepts before transitioning from the Z distribution going to the T distribution. Now, last time class, as we recall, we computed or we compare one sample compared to the population by simply when we have a large group. Meaning of large group is that we have the population, and then there is a sample group taken from the population, and we compare the mean of this population to this one. But the assumption there is that the sample group should be large. At least the rule of thumb is that the sample group should at least be 30 samples, 30 or more. But lower, less than 30, the Z distribution is no longer applicable. There is a variation why it's no longer applicable. There is a better test statistics that is applicable or much useful when it is less than 30. Okay. Now, very quick. Last time we estimate the standard deviation. Estimating standard deviation meaning to say we estimate the standard error. We estimate the standard error meaning to say the standard deviation of the sample by simply considering or when we have the population mean. Example, our standard error was like this, and then the population standard deviation divided by the square root of the sample size. This is for our standard error. Now, in the event that this is not available, okay, so we can only compute this one. Remember our z value for the large z test, that is mean minus the population mean of the sample population mean divided by the sigma sub x bar. So this is our formula. But the event if our standard deviation is not known, we can actually estimate also our standard deviation by using this formula. Take note, there is an assumption here. This assumption will only take hold with us trying to claim that the standard deviation or the deviation of our population, deviation of the sample did not change over a period of time. For example, the standard deviation before and up to the present of the sample is just the same. So with that assumption, we can consider now, we can estimate our standard deviation for the population using the standard deviation of the sample. Take note, we collected the sample, right? I mean, we collect the data from the sample. As we determine the sample size and then we collect the data from the sample, we took the mean, and at the same time, we can conclude the standard deviation. With the assumption that the deviation of our distribution did not change from the population up under the sample, we can consider the sample standard deviation to be our standard deviation to be considered to solve for our z-score. So what I'm saying is like this. Example, instead of using this one, in the case or in case our standard deviation of the population is not known, then we can make an assumption that with the consideration that the standard deviation of the population did not change over the period of time, we can take the standard deviation of the sample size. So instead of using this one, we will have S sub x bar is equal to standard deviation of the sample divided by the square root of the sample size. So this is standard deviation of the sample. So what we're talking about here is that we're not going to, since the standard deviation of the population is not known, and holding with the assumption that the standard deviation of the standard deviation did not actually change, then we can take the standard deviation of the sample group. So instead of solving this one, we can already adapt and make changes to our the computation of our z-score. And how do we do that? We have z equals x bar is minus mu. Instead of using the sigma sub square or sigma sub x bar, we can use the s x bar. This time, the estimated standard error here was computed based on the sample standard deviation and not population standard deviation. I hope that's clear. Now, let us try to look at this example. This is large sample. This is actually for the large sample Z test. Large sample Z test. With the assumption that, I mean, with the condition or when the situation arises that the population standard deviation is not known, for large sample Z test, we can short, we can somehow short, we can somehow make an alternative formula such as this one for large sample Z test, considering with the assumption that the standard deviation of the population did not change or the deviation did not change. So we adopted the standard deviation of the sample to represent the population standard deviation, with the assumption that actually the standard deviation of the population is just the same with the standard deviation of the sample group. Okay, let's take this example. So let us apply the large sample z-test, which is this formula, the large sample z-test, with the following given. Our mu is 63. This is about the psychotherapy phase. Okay? So we can plug in the following values. We have our population mean. The population mean for the psychotherapy is 63. Okay? That's their hourly pay. For example, this is in way back how many years? $63 is the average fee for all the psychotherapy. Now, the sample mean is 72. So that is the sample mean, 72 hourly the per hour payment for psychotherapy session. Now, the sample group for this one, the mean was taken from a sample size of 100. And then with the standard deviation of 22.5, for example, per hour. Let's say the currency here is dollar. Now, we would like to, with the unbiased standard deviation of the 100 therapies in our sample, normally you would have to calculate S yourself from the raw data, but this, to simplify matters, I am giving you, for example. Okay, now, in an actual event, from the 100 sample here, large group, we can simply, 100 here, we can compute this one and then this one based on the result from the raw data. But in the event here, we just simply make an assumption right away without the actual computation, since where this is for the purpose of example. But actually, you can really solve for this one. Step 4 in our test hypothesis, you can collect and gather your own data, and then once you have it, solve for the average, and then afterwards you solve also for the standard deviation, and then you try to do that. But in this case, we skip that part, and we have already here the assumingly the result of our mean and then our standard deviation. Now let us solve for our z score. Okay, and then we will compute for this one. Let's start. First is we are going to estimate our standard deviation, the estimated standard error. This is our given formula. We do not know the population standard deviation, so therefore we're up to use this one. So we have S x bar is simply S divided by the square root of n. Our S is 22.5 divided by the square root of 100. So applying this formula with that one, so we have Z. Our sample mean is 72 minus the population mean is 63 divided by 22.5 divided by square root of 100. Oh, come on, you solve. What is the Z score? The answer is 4. If we're going to decide now if this is the computed Z for this large sample group or this large sample Z test, if our critical value, for example, is 2.5, and this is the computed Z, thus our decision is we reject the null hypothesis because our computed Z is greater than the critical Z. So if in a diagram, example, if the critical Z is at 2, okay, so since this value is found in this area, in the rejection region, thus our decision and step 6 is reject the null hypothesis. Meaning to say, the result is significant. Okay? Because we rejected the null hypothesis. Now again, this is only applicable, I mean, this is going to happen, will take place if the population standard deviation is not known, and then we're dealing with a large sample z-test. Large sample z-test. Large sample z-test, no wonder, because you look at our sample size, it is 100. Now, this is just an example. Your z-score is 2. And our computed z is, this is the critical z, the boundary. Since our computed z is 4, for example, so it falls on the rejection region. Thus, our decision is we reject the null hypothesis with the decision that our test statistics is significant. Let's go to t distribution. This was z distribution. Now, let's move to t distribution. What is this so-called t distribution? T distribution class is simply, this is another test statistics that we can impose. But this is much applicable when our sample size is less than 30. For example, your sample size is 10, 16, less than 30. Because the assumption there for the large z-test is that when the sample size is more than 30, then you can use it. But actually, t-distribution is still applicable if you go beyond 30. But ideally, z-distribution is no longer, it's no longer appropriate to be your test statistics when your sample size is less than 30. This is the best statistical analysis that you can use. Now, what's the story about the t-distribution? Let me just read to you this one. Okay, the story about the large sample z-test, take note, the large sample z-test is why it's no longer accurate when our distribution, when our sample size is less than 30, it's like this. Now, take note, earlier, when we do not know the population standard deviation, we estimate our standard deviation using the standard error. We estimate it using the sample standard deviation, right? The S sub x bar. In the event that our sample size is less than 30, we can make the estimation. We can come up with estimation using the standard deviation of the sample to represent the population standard deviation, with the assumption that when it's large sample size, it would resemble to the population standard deviation. Because remember, the larger your sample is, it would always move further, move closer and closer to what is the actual standard deviation of the population. But if your sample size is too small, then it's expected that it cannot resemble, it's inaccurate to use the sample standard deviation to be our estimated standard error. It's because the sample size itself is very minimal. It's very far from the population standard deviation as our estimated standard error. That's why when our sample size is less than 30, it's really inaccurate to use it with the idea that we use the Z, we use the X sub bar, the S X sub bar to be our standard error, the estimated standard error. Since the sample size is very small, no wonder it's really inaccurate because it is quite far from what's the original standard deviation of the population as estimated. Okay? So that is the reason. Now, the story of the t-tests. There was a problem confronting William Gossett in the early 90s when he was working as a scientist for a Guinness brewery company. So this person, William Gossett, he works in a Guinness brewery company. So it's like a beer company in England. It was important to test samples of the beer and draw conclusion about the entire batch. But practical considerations limited the amount of sampling that could be done. Gossett most enduring contribution to statistics was finding a distribution that could account for the error involved in estimating standard deviation of the population from estimating the standard error for the sample with a small sample size. Due to his company's restriction about publishing, Guinness was afraid that other beer companies would make use of Gossett's work. He published his findings under the pseudonym Student. Therefore, the distribution whose usefulness Gossett discovered, for which he used the letter T, came to be known as Students' T distribution, or just the T distribution. Gossett's publication preceded the work of R.A. Fisher mentioned. Okay, so the story was like this. If I'm gonna summarize it, it's like this. William Gossett, a scientist of a brewery company, the Guinness Brewery Company in England, he came up with a distribution that would represent the error in estimating the population standard deviation from sample standard deviation. So it's like this. Uh, Due to some restriction, he cannot test the entire batch of the production of the brewery or the beer. So there was just a very more sample size, example, less than 30, and he took a sample and he developed a distribution that would somehow identify the error in estimating the population standard deviation compared to the sample standard deviation. That is what happened. The event that the Guinness Brewery Company do not want Gossett to publish his work. It's because technically it can be copied by other company, and then of course for competition's sake, so they reprimanded Gossett to publish his work. But because of this contribution of Gossett to the field of statistics, he still decided to publish it by a pseudonym Student. So instead of using William Gossett to be the proponent of this distribution, the T distribution, he uses the pseudonym Student. So that's why in the old times, or William Gossett is known as, I mean, the T distribution is also known as the Student's T distribution. Students, it's because that's the pseudonym where William Gossett used this T distribution when he registered it or when he published this work. That's why T distribution is also known as the Student's T distribution or Student's T distribution. Okay? Student's T distribution. And now that's the story why it's called Student's T distribution. Okay? Now, the formula for student T distribution is basically T is equal to the mean of the sample minus the population mean divided by our estimated standard error, which is S over the square root of N. That is our formula. Of course, we already tackled as to what or how this is solved. Or simply, that is T equals mean of the sample minus the population mean divided by Sx bar. Okay, that is our formula. Now take note, this will take place because our sample size here is very small. So instead of using the standard error of the population, that's why we use the T distribution now. Because T distribution was actually designed to estimate the standard error or to estimate the estimated standard deviation of the population with a minimal sample. So this is our formula. Now let's take a look at this one. First here, the T distribution is not going to use sample size. Why? Remember, in the event or in this case for the T distribution, our sample size is very small. Okay? So it is inaccurate to use it as our basis for identifying the distribution. That's why T distribution is actually distinguished by using the so-called DF. What is DF? DF means degree of freedom. Now, why T distribution was actually based on degree of freedom? Take note, the estimation here was based on the standard deviation of the sample. Okay? The estimation here, since the sample size is very small, using T distribution as it is designed, take note, the standard error here, the computation for this one is simply n minus 1. Remember that when we compute our variability or the standard deviation last time for the sample, for minimal sample, is we have n minus 1. This is at least divided by n minus 1 for the standard deviation. No wonder that the degree of freedom is simply df is equal to n minus 1, with the assumption that the idea here was taken for the concept of solving for the standard deviation, where the standard deviation is found by simply dividing it by n minus 1. Okay? So, when we distinguish the t distribution, we would always look at the degree of freedom. Now, class, in identifying the t distribution or using the t distribution table, we will get the t critical or the t compute, the t tabular by using the degree of freedom, alpha, and the tail tests. The tail tests used in your problem, whether it's two-tailed or one-tailed. Because basically, if you look at the table, there is already a designated t value for two-tailed tests and one-tailed tests. You look at your t table. So for example, if our sample size, where n here is a sample size, if our sample size is 20, our df, n equals 20, our df is n minus 1 equals 20 minus 1, you have 19. So 19, let's say our alpha is 5%. 5% alpha, and then it's two-tailed, let's say two-tailed. Can you refer this to the table? What is the T critical? By the way, we can write this T as like this. T.95. The 95 here is the so-called the confidence level. Since our alpha is 5%, and the confidence level at one-tailed and two-tailed test with a degree of freedom of 19 is equal to. So refer to the table. Go ahead. Check your table. Everyone, you check your table. Look for the confidence level 95% two-tailed. And then from the degree of freedom, look for 19. What is the T critical or the T sub 95? What is the value? 2.093. Yeah, that's the correct value. 2.093. Now let's try to have another one. What about if the degree of freedom is 6? A two-tailed test, 10% alpha. What is the T critical? So that is T.90. What is the T critical? Our degree of freedom is 6. And then our alpha is 10% at two-tailed. Using two-tailed tests. Two-tailed test, 10%. What's the value? Huh? Our degree of freedom is 6. And then two-tailed, 10%. It's 1.943. So that's correct. Okay? So at least you know now how to use the T table. So that's why, in using the T table for identifying our T critical, it's simply we need our degree of freedom. At the same time, we need our alpha, and then we need to identify also whether it's two-tailed or one-tailed test. So now let's take this example. Using the T distribution, it's one sample T test. Okay, let us solve this one. The psychotherapy fee, still the psychotherapy fee, but this time our assumption, our sample size is 25. Take note, it's less than 30. And then let's say our standard deviation for this one is the same. Our S is 22.2. Standard deviation is 22.2. And then our population mean was still $63 per hour. That's the psychotherapy fee of $63. And then the mean for this group is the sample group, the mean of this group 25 is still $72 per hour. Now let us solve for our t value. So first, that's t equals x minus mu divided by s square root of n. So you have our mean is 72 minus 63 divided by 22.5 divided by 20, the square root of 25. What is our t value? What is the t value? What is the computed t? If this is our situation. Okay, now
Yes,
let's
sir.
take a look at this one. This is the computed t. By the way, this is our t computed. So let's say it's t compt is equal to 2.00. Now, let us try to compare this to our tabulated or our T critical. So let's say T crit. For the T critical, let's make an assumption we have alpha at 5% because statistics is in the accepted alpha for psychology is 5%. And then we have two-tailed. What is our T critical? Look at the table. Yeah, that's correct. That's 2.064. 2.064. Now, to make a decision, you are going to compare this. Example, T compt is less than T critical, which is, by the way, 2.00 is less than 2.064. So the decision here is what? If you look at the diagram, our mean here, our T critical is 2.064. But our T, this is the rejection area, okay? But our T critical or our T computed somehow falls on this side, okay? Which is 2.064. So it did not somehow landed in the rejection region. So if this is the case, our decision here is we fail to reject, fail to reject HO. Because in other words, our T computed did not land on the rejection region in our um, map for distribution for the T distribution. Again, we reject the null hypothesis when our computed T is less than the T critical. So our goal, in order for us to reject the null hypothesis, is that our T computed should always be greater than the T critical, so that it will land to our rejection region. Okay? Any question? By the way, our decision here is we fail to reject the null hypothesis because our T critical is greater than our T computed. What about if we will change the type of test? Let's say we have one-tailed tests. Do you think we still have the same decision? You look at the T critical value at one-tailed, 24 one-tailed. So that's 1.711. Our T critical is 1.711. And then our T computed is 2, somehow, which is here, 2.00. So it landed in the rejection region. So our decision now will become reject the null hypothesis. Okay? So you notice, as we change the type of test from two-tailed to one-tailed, then our decision actually changes from fail to reject the null to reject the null hypothesis. Correct? Because at one-tailed test, our critical value is 1.711, while 11, while the computed t is 2. Therefore, the computed t landed in the rejection region at one-tailed test at the same alpha value. So our decision is reject the null. But at two-tailed tests, the same alpha 5%, we fail to reject the null hypothesis because the critical t happens to be greater than the computed t. But at one-tailed test, we notice that the critical t is less than this is the situation at one-tailed test. It became t const is greater than t critical at 0.05 alpha one tail test. See, changes happens as we change our tail tests from one tail to two tail. Actually, you can make no. You have to distinguish. You have to identify whether you're going to use one tail or two tail. That depends upon the situation of the problem. If the problem would say there, if it's non-directional, meaning to say um, there is no instruction whether it's greater than or less than. So, but the claim was just there is a significant difference. So it means to say it's two tail. But if we say that it's greater than, it's expected that it's one tail test because the idea there is greater than. So there is a one rejection region and it's found on the left side of the mean. So right side of the mean rather. So that means to say it's one tail test. Actually, it's not decided most of the time. You will see there one tail to two tail. You have to figure it out from the problem. And the problem would say that suppose that the mean of the sample group is greater than blah blah blah. So it means to say it's directional. The intention here, I mean the assumption is that we somehow expect to reject the null hypothesis on the right side of our mean in our null distribution. So it means to say it's a one-tailed test, rejecting the null hypothesis on the right side of our mean. If we notice earlier, we computed the z, right? The same problem, the z was computed with a sample size of 100. And our z value was 4. Remember that, the previous example? And then when we computed our t here with a sample size of 25, our t was 2. It's actually half of the z value. So you notice there was a movement or changes for our t value as we reduce the sample size. But still, it's possible to look for the variability, or at least look for the situation. Okay, for t distribution, as they are all about the mean, they are highly affected by outliers. You know what's outliers, right? Outliers are simply the values that are too extreme. It's either too small compared with the majority, and then, or it's either too large. For example, if we're talking about example hourly fee, if one in a sample size, the majority of your distribution clustered around the mean, but the fact that there is an hourly fee, like for example, overcharging of, in from the rest of the group, that there is one extreme value of 100, it would actually affect the distribution. So it could alter the result. Instead of rejecting the null hypothesis, it could alter the result to accepting the null hypothesis because of the outlier. So that's the role of outlier. Outlier can actually affect the significant result of our test, our t distribution test, because of its impact. Okay, that's the impact of the outliers. Okay, the note there that perform the appropriate one-tailed test, although normally it will not be justified. It will not be justified because we're always encouraged to use two-tailed. But for the purpose of example, in this case, we are going to take the hypothesis testing at one-tailed tests. Now, how do we interpret the problem? It's like this. So there is an assumption that we're asked whether is there, where is that? If the population mean is 36, that's the introversion score of the population mean. Are the serial killers significantly more introverted than more introverted at 5% level of significance? So it's like this. So from the general population, that refers to everybody. So the introversion score of the average introversion score for the general population is 36. Okay, that's their average score for the introversion tests. And then we're trying to test the hypothesis that the serial killers, okay, the word here is serial killers, those who committed a serious serial killers in short, whether they are more introvert than the general population. So that is our assumption. Again, what's the first step of our null hypothesis testing? First step is, okay, we will state the null hypothesis. So how do we state now the null hypothesis in this situation? That is our problem. We were given the instruction. What is our null hypothesis? Remember, we will set up our null H sub O, and then we have our H sub A. For the H sub O, we will state here our population mean is equal to 36. That's our population mean. In this problem, it's 36. This means to say that there is no significant difference between the mean of the sample group and the population group. Okay, that is our hypothesis, null hypothesis. Meaning to say, the mean of the mean score, introversion score of the serial killer does not actually deviate far from the mean of the introversion score of the general population. While the other one, the alternative, the question here is, if the population mean is 36, are the serial killers significantly more introverted? Take note, the clue there is more introverted. So in this case, we would say that the mu is greater than 36. Meaning to say, the introversion score of the randomly selected serial killers, or the serial killer groups, their introversion score is greater than the introversion score of the general population. So our equivalent statement here is there is a significant difference between the mean of the sample group, and the general population. Okay? We stated now our two hypotheses. Now you notice this is directional. No wonder that the suggestion here perform the appropriate one thing. One thing because we assume to reject the null hypothesis somewhere above the mean. Okay? Because we're trying to, the problem here is trying to hypothesize that the introversion score of, that the serial killers are more introvert than the general population. The general population, that includes us. That means to say, those who are considered as serial killers, they are more introvert than the average or than the regular population or the general population. So we stated now our two hypotheses. Okay, we have the null hypothesis, meaning to say there is no significant difference between the mean of the sample group and the general population. While the alternative, which is mu is greater than 36, it means that there is a significant difference between the mean of the sample and then the general population. Okay, so you notice and we set up already our two hypotheses. But the specific meaning of this one, that actually we can be more specific with this one. We will say that the mean of the sample group is greater than the mean of the population. Then the other way of stating this one. But I am trying to make it a more general statement. There is a significant difference between the mean of the sample group. In fact, the implication of this one is that that the mean of the serial killer is greater than the mean of the general population. Okay, these serial killers were actually serving life sentence. So if they're like in a prison cell, serving life sentence, meaning to say they can no longer go out from being in prison. So with that saying, our sample size is less than 30. Therefore, we cannot use z-test, large sample z-test, but rather we can use one sample t-test. So our test statistic here is t tests. And then we will assign our alpha. Our alpha here is 0.05. And then this one, we also decide our DF. 14 minus, or that is n minus 1 equals 14 minus 1, 13. Our degree of freedom is 13, t-test, and then alpha is 0.05%. Take note, it's one-tailed test. It's because of our alternative hypothesis, which is directional. Actually, this is supposed to be, there is, or that, anyway, our symbol here is directing us that there is a greater mean for the sample group compared to, because the statement there is a significant difference is actually like two-tailed, because it does not signify a certain direction. So there is no, it should not be there is, but the mean of the sample group is greater than, let's just change this one, because our alpha, our hypothesis statement here must coincide with our symbol. The mean of the sample group is greater than the general population, than the mean of the general population. Okay, as our hypothesis is concerning. So in this case, we're also our n here is 14, and then we assume that we collected already the data, because in the actual sense, you really have to go and look for the 14 serial killers and then get their scores and then do the computation. But anyway, this is just for example. We know that what is supposed to be done in step 3 is that you identify your sample size and then collect the data from the sample. Step 4, what is the step 4?
Find the region.
Okay, our diagram. The mean, the mean for the population's sample group, I mean the serial killer is, mean score is 36. So this is 0. The 0 here implies 36. Take note of that. And then let's illustrate our T critical. What must be our T critical so that we will know our standard for comparison? What is the T critical? What you're going to, what you need, we have already here our type of test. We have the alpha, we have the degree of freedom. So what is the T critical? Take note, T critical is found here. It's because of the symbol directional, and it's found in the greater side. Okay, you give me the T critical using the T table. 1.7771 or 1.711?
771, sir.
Okay, 771. So this is our T critical. Now take note, in order to reject null hypothesis, our T computed must be greater than this, so that it will fall in this area, the shaded region here. Okay, as our T critical is 1.771. So we already illustrated our rejection region. Step 5 is we will do the computation. So that's T equals mean of the sample minus mu divided by S over square root of n. So our mean is, what is our mean for this sample? We have 42, right? 42. What is the population mean?
36.
36. Then divided by, divided by, what is the standard deviation? That is 6.8. Divided by the square root, our sample size, 14. What is the computed value from there? So good. 42 minus 30 divided by 6.8 divided by the square root of 14. What's your answer? You have 3.0. Now, our last step, step 6, what's our decision?
Make statistical decision.
We will now make our statistical decision. Since T compt, that is 3.30 is less than or less than is greater than the T critical T3 of 1.771, thus reject the null hypothesis. That's our decision, correct? Since the since the T computed that is 3.30 is greater than the T critical of 1.771, thus reject the null hypothesis at 5% level of significance. We can actually complete. Thus reject the null hypothesis. I mean, correct this one. At 5% level of significance, thus reject the null hypothesis. Okay, that's our decision. Since the T computed that is 3.30 is greater than the T critical of 1.771 at 5% level of significance, thus reject the null hypothesis. That's the end of the 6th step. And then after that, your interpretation. What will be your interpretation based on that? Since we rejected this one, that there is no significant difference between the mean of the sample and then the general population. So this is what is being carried out. Our conclusion is that, therefore, let's answer the question. Therefore, the serial killers are found to be significantly more introverted at 5% level of significance compared to the general population. So your conclusion, therefore, in the conclusion phase here, you would say that, therefore, since this is our decision, therefore, the serial killers are found to be more significantly introvert at 5% level of significance compared to the general population. Okay, let's write that. Therefore, the serial killers are found to be more significantly more or significantly found to be significantly more more introverted than the general population. So it's like saying now that the serial killers are more introvert compared to the regular individuals based on our findings. So again, if we recall or recap, step 1, we set up our null hypothesis, which we say that mu is equal to 36. That means to say there is a significant difference between the mean of the sample group and then the general population. Well, the alternative is that we have mu greater than 36, meaning to say the mean of the sample group is greater than the mean of the general population. And then step 2, t-test. We are going to use t-test here, considering that our sample size is only 14, with alpha 5% level of significance and the degree of freedom is 13. Step 3, we collect and gather the data. Step 4, we set our rejection region. We found out that at 1.7, our T critical is 1.771. And then we computed our T in step 5. We found out that our T computed is 3.30. Thus, our decision is the T computed Since the T computed that is 3.30 is greater than the T critical of 1.771 at 5% level of significance, thus we reject the null hypothesis. With the conclusion that the serial killers are found to be significantly more introverted than the general population. That's the end of our hypothesis testing. Question. Now, if we try to alter our given, what about we will change our null hypothesis to this. So we're not going to do, we will make our null hypothesis to be like this. So of course, our statement here, there is no significant difference between the mean of the sample group and then the general population. That is the equivalent statement if our alternative is mu is not equal to 36. What will be our decision? Reject. Are we going to have the same decision or not? What must be our T critical? If this is now our example, this is our situation. I already changed the from directional hypothesis to non-directional. What must be our decision? Are we still going to end up this one or not? What is the T critical if it's already non-directional, two-tail?
2.160, sir.
Yeah, so what is the decision? Can you please come up with say your statement or your decision in this statement form, changing the given. Could someone do that for us? Let's call somebody here. Let's have.
Still reject man gyapon, sir.
Can you please state your decision once we have already two-tailed? The rest of the information are the same, and we change our tailed hypothesis to the non-directional. With the T critical of 2.160, what is our decision? And then our T computed is still 3.30. Anyone, can you please state your decision now after we change it from 30 from non-directional from directional to directional, from directional to non-directional rather. So we will say here, since the T computed that is 3.30 is greater than or less than, our T critical, T crit is 2.160.
Same para sa same ra.
So
Same
we will say here, since the T computed that is 3.30 is greater than the T critical of 2.160 at 5% level of significance, thus decision is reject the null hypothesis still because 2.160 is still less than 3.0. So if you draw the diagram, it would appear to be like this. This is 2.160. This is the rejection region. But still, 3.30 is on this area, on the rejection side. That's why still our decision is reject the null hypothesis. A two-tailed, let's still like this, mu non-directional, and then our alpha is 0.002. What's the decision? Come on, what's the decision? 0.002, 36, 13. What will be your equivalent your decision? Since, Miss Alon, state your decision. If our test is non-directional, and then our alpha is at 0.002, meaning to say it's less than 1%. It's 0.20% alpha. What is the decision? You can check it from the table. This time, we changed now the parameter. Instead of directional, we made it non-directional, meaning to say it's two-tailed. And then we set our alpha at 0.02 with our degree of freedom of 13. And then this is the computed T. Now tell me what's the decision.
answer ka na.
State it this way.
So since the T computed that is 3.30 is greater than the T critical of 2.650.
No, that's not correct. Your T critical is not correct.
Ay, 0.002 di. Wait, sir.
Review it. Yeah, that's the correct one, Iburan. 3.852. Again, state it.
So since the T
Wait.
computed,
You just remove the word so. You say have so, you have since. That's already redundant. I mean, too much.
okay, since the T computed that is 3.30 is less than the T critical of 3.
3 point.
3.852 3.852 at 5% level of
Wait,
significance.
at 5%? You
I
change
mean,
already your alpha.
sorry, sir.
At
2% level
no, that's
of
not 2% because if you round this one, that's not even 1%. It's actually 0.2%. You can just say it this way. You can just use this one.
At 0.002% level of
You
significance.
remove the
Thus,
percent. Wait. If you will use this one directly, you don't need to use percent because this is in decimal. If you wanted to convert this one in decimal, in percent, that's or 0.2%. That's its equivalent in decimal because you have to move the decimal point to the right 2 places. So that's 0.2%. So not even 1%, less than 1%. Again, say it again from the top.
since the T computed that is 3.3 is less than the T critical of 3.852 at 0.2% level of significance. Thus, we accept the null hypothesis. We failed to reject the null
Yeah, that's the right word. We fail to reject the null hypothesis. So what must be the conclusion? Since that's the decision, what must be the conclusion?
conclusion would be accept the null, sir.
No, that's not the conclusion. The conclusion should be this one, answering the problem. How do you say that? Take note, this is non-directional. So, therefore, the serial killers are found to be not significantly more introverted than the general population because we failed to reject the null hypothesis stating that there is no significant difference. So it's like saying that the general population's introversion score is just the same with the introversion score of the serial killer group. So I would say that the serial killers are found to be not significantly more introverted than the general population. No, I would like to ask if this is, let's go back to the original, this one, the original uh, hypothesis. And then this is the second one, which earlier classmates said that since the T computed that is 3.30 is less than the T critical of 3.852 at 0.2% level of significance, that's the Jack null hypothesis. That's the two cases. At the first, I mean, using the first scenario, which is this one, what type of error could you possibly commit with this result?
Type 1 error, sir?
Sir.
Okay, so there is a risk of committing type 1 error in this decision. What about the last decision? We're in the decision in this situation, wherein the decision is we fail to reject the null hypothesis. What type of error could have been committed?
Type 2, sir.
Why?
We failed to reject Mansur, so supposed to be.
Okay, we fail to reject the null hypothesis when it is supposed to be rejected. Okay?
Yes, sir.
Type 2 error. So you have to take note what type of error is more likely you're going to commit doing a statistical tests.